Assalamualaikum and hi everyone. In this video, we are going to discuss some of the questions related to equilibrium constant. Okay, so this is tutorial 6.1 and 6.2, question number 10. So let's read the question first. Nitrosyl bromide decomposes to form nitrogen monoxide and bromine. Okay, the equation is given. Okay, if 2.0 mole of nitrosyl bromide in 1 liter, okay, volume, decomposes to give 0.09 mole of bromine. Okay, we have two number of mole here. Okay, at equilibrium and the temperature is 77 degrees Celsius. Determine the equilibrium constant Kc and Kp. And for B, determine the degree of dissociation. Okay, we have two number of mole here. The first one is number of mole of NOBr, which is the number of mole of reactant at initial. Okay, you need to identify the number of mole given is number of mole initial or number of mole at equilibrium. In this case, okay, the number of mole of reactant given is mole initial. Okay, and a number of mole of the product, which is Br2, is number of mole at equilibrium. Okay, so in order to calculate the Kc, we need to have the concentration of all species at equilibrium. Okay, so how to relate the initial mole of reactant to the concentration at equilibrium? Okay, we should draw an ICE table. Okay, ICE table. So every time you want to draw an ICE table, you always have three options. Either you want to use the ICE table in terms of number of mole. That means you can use N initial, N change, N equilibrium, and lastly calculate the concentration at equilibrium. Or you can use ICE table in terms of concentration. That means you calculate the concentration initial first from the number of mole initial given, and then the concentration change and concentration at equilibrium. Okay, this is the ICE table in terms of concentration. And last one, you also can use ICE table in terms of pressure. Okay, if you are given with number of mole initial, and you have the temperature, you have the volume, okay, you can calculate pressure. Okay, if the question asks you about Kp, okay, P initial, P change, and P equilibrium. Okay, so in this case, I want to use ICE table in terms of concentration. So we need to calculate the concentration initial. So the unit is molar. So 2 mole divided by the volume. Okay, 2 molar. Okay, 2 mole per liter. Okay, so this is the concentration initial for the reactant. So at initial we don't have the product, so dash. Okay, before the reaction start, so we only have the reactant, therefore the product is 0. Okay, so once the reaction is started, okay, what happened to the reactant? The reactant will decrease in concentration. Okay, minus 2x, since the coefficient for the reactant is 2. Okay, So the product will increase in concentration. So plus 2x for NO, okay, and plus x for Br2. Okay, depends on the coefficient of the species. And then the concentration at equilibrium. Okay, you can use concentration E for, or concentration EQ, okay, stand for equilibrium. So concentration at equilibrium is 2.0 minus 2x, and then this one is 2x and x. Okay, and the question gives you the mole of bromine at equilibrium. Okay, that means here x is equal to 0.090 mole. Okay, divide by the volume 1 liter. Okay, so x is equal to 0.09 molar. Okay, our x is in terms of concentration. Okay, because we use ice table in terms of concentration. So you can calculate concentration of NO, 2x, 2 times 0.09. Okay, we already have the x value. So here is 0.18 molar, and concentration for NOBr is 0.09 equals 1.82 molar. Okay, so now we have all the concentration of all species. Okay, we can calculate the Kc now. Just substitute the value in Kc expression. So Kc equals concentration of NO squared times concentration of Br2. Okay, concentration of product over reactant. So NO Br squared. Okay, just substitute the value just now. Make sure it is the concentration at equilibrium. So Kc is 8.8 exponent negative 4. Okay, so to calculate Kp, we are going to use the formula that relate Kp to Kc. So Kp equal to Kc RT to the power of delta N. So in this case, delta N is 2 plus 1, okay, minus 2. Okay, the number of mole of product minus number of mole reactant. So 2 plus 1, 3, 3 minus 2 equals 1. So the power for RT is 1. Okay, substitute our Kc, 8.8 exponent negative 4. Okay, make sure you know we use R, gas constant 0.08206. Okay, the constant is given in exam. Okay, T, make sure T is in Kelvin. Okay, so R times T to the power of N, delta N. So N is 1. So the value of Kp is 0.025. Okay, for question B, calculate the degree of dissociation. Okay, the formula of degree of dissociation, or alpha, equals concentration dissociated over concentration initial. So in this case, okay, we can refer to the concentration change. Okay, this is the concentration change for the reactant, 2x. Okay, so this is the concentration dissociated. Okay, 2x. Okay, if the coefficient is 3, so here minus 3x, so concentration dissociated is 3x. Okay, so we take 2x and the concentration initial is 2. Okay, so 2x over 2.0. Okay, the x value just now is 0.09. Okay, so we can calculate the degree of dissociation. It is equal to 0.09. Okay, that's all for question number 11. Sorry, question number 10. Okay, thank you.